Try asking your AI system to find out who approved the budget for the project assigned to a specific employee's manager. In a vector database, every fact is an independent point floating in high-dimensional space. A semantic search beam finds relevant points, but empty space remains. No structural connections exist. Natively mapping relationships snaps these points together, flattening the 3D space into a precise context graph. Standard retrieval augmented generation forces the model to infer relationships from disjointed text chunks. A graph explicitly defines those relationships. Because the connections are already mapped out, the AI can traverse from the employee to the manager to the budget approval in milliseconds. Agentic systems require a memory architecture that defines relationships as clearly as it defines the facts themselves. In a production environment, enterprise systems manage thousands of interconnected data points, organizational hierarchies, project dependencies, and customer relationships. This scale exposes the first failure mode of flat memory stores, multi-hop reasoning. Flat stores cannot reliably chain facts across multiple connected entities. If you ask the system to identify the manager of the person assigned to an overdue task, vector search retrieves individual facts about the task and the person, but it fails to trace the path back to the manager. The second failure mode is contradiction handling. Vector stores hold conflicting facts simultaneously because they lack a native mechanism for conflict resolution. If a session logs an employee on Team Alpha and later on Team Beta, a vector database returns both as equally valid embeddings. The third failure mode is temporal reasoning. Standard vector search has no concept of time-bounded facts. It retrieves whatever matches semantically, regardless of when it was true. If you ask who was on a team last quarter, the system returns the current roster, just because the words match. Without logical constraints, contradiction detection, and temporal awareness, flat RAG architectures frequently produce hallucinations when scaling enterprise data. We address these failures by moving away from flat text chunks. A context graph replaces isolated facts with a structured map of knowledge built on 3 core components. Look at this structural model. The first component is a node. Nodes represent distinct entities, like people or projects, and possess specific types. The second component is an edge. Edges are directed, labeled connections that give the relationship between nodes a rigid meaning. The third component is properties. These are key value attributes attached to both nodes and edges to store metadata, like dates and statuses. Unlike traditional relational databases, traversing these connections is a primary operation. You bypass the need for complex, resource-heavy SQL table joins. This graph schema is also flexible. Developers can add new node and relationship types as fresh knowledge arrives without database migrations. Explicitly mapping nodes, edges, and properties provides the AI with a deterministic world model. To implement this architecture, you need a system that transforms unstructured conversations into structured graphs. Zep Graffiti acts as the ingestion engine. It monitors your agent's conversations in real time, extracting entities and their relationship edges. Those extracted architectures are stored in Neo4j, a production-grade graph database.
The pipeline is automated. When a user states a new fact, Graffiti parses the text, updates the specific node, and draws the corresponding edge directly into Neo4j. Graffiti serves as the conversational brain that comprehends structure, while Neo4j serves as the memory that holds it. Production-grade reliability is achieved through a feature called the bitemporal model. The real world and an AI system's knowledge of that world are rarely synchronized. The system needs to distinguish between when an event happened and when it learned about that event. As shown in this diagram, every fact receives a dual timestamp. The first is t-valid. This marks the exact moment a fact became true in the real world. The second timestamp is t-invalid. This marks when a fact ceases to be true. If the fact is currently active, this stamp remains null. If Bob leaves the project, the system handles the contradiction by updating the old timestamp and spawning a new path to his current assignment. The old data is preserved as historical record. This mechanism manages context rot by allowing the agent to prioritize currently valid facts while maintaining a record of those that have expired. This design enables temporal queries. Agents can pull historical snapshots by querying specific date ranges, retrieving exactly what the network looked like at that time. The bitemporal model provides a paradox-free context window for the AI and a structured, auditable history of every change. With this bitemporal structure in place, how does an agent pull answers out of it? Look at this network visualization. First, semantic search finds conceptual starting points in a general cluster. Second, lexical search executes exact keyword matching to pinpoint critical identifiers. Third, graph traversal walks explicitly along typed edges to discover connected data, revealing direct reports and projects. Developers can control this traversal, forcing the search to only follow specific relationship types, such as direct reports, while ignoring irrelevant paths. Graffiti merges all three modes into a single unified query. It evaluates the starting points, matches the keywords, expands the context, and ranks the results by relevance and connectivity. A single hybrid sweep surfaces deep context that flat search cannot access. Hybrid retrieval combines conceptual flexibility with the structural logic of a knowledge graph. The bridge between the AI and the database is Cipher, the declarative graph query language used to execute these hybrid traversals. Cipher syntax is highly readable. It reads almost like English, making complex relational pattern matching intuitive to review. Operations that would require nested SQL joins in a relational database translate to simple one-line queries in Cipher. The agent receives a user prompt, generates the Cipher query, and executes it against Neo4j to pull the necessary structured data. Grounding the AI's response in explicit relationships reduces the likelihood of hallucination compared to systems relying on inference alone. Context graphs upgrade an agent's memory from isolated data fragments into a coherent, time-aware structure. By adopting a structured graph architecture, we transition AI agents from probabilistically guessing our world to deterministically mapping it.